Hello and welcome to Late Night Physics. Before we begin tonight's journey, take a moment to gently support the channel. If you enjoy calm explorations of the universe like this one, consider liking the video and subscribing. It helps the channel grow and allows more curious minds to drift into these quiet corners of science. And while you're settling in, I'd love to know where in the world you're watching or listening from tonight. Are you somewhere beneath a city skyline where light reflects off glass towers? Or perhaps far away from the glow of streetlights, under a dark sky where the stars feel almost close enough to touch. Wherever you are, the light reaching your eyes right now has travelled an extraordinary journey. Some of it may have crossed a room, some may have travelled from the sun, a journey of about 8 minutes. And some of the light in the night sky began its voyage thousands, millions, or even billions of years ago. Every beam of light carries with it a silent message about the universe. But there is something even more mysterious about light than the journeys it makes. No matter where you are, no matter how fast you are moving, light always travels at exactly the same speed. Roughly 299,792,458 meters per second. This number appears everywhere in modern physics. It links space and time, energy and mass, cause and effect, and even the limits of information in the universe. In fact, the speed of light is not simply a property of light. It is a property of reality itself. Tonight, we're going to slowly unpack one of the deepest questions in physics. Why does the universe have this speed limit? Why is there a maximum speed at all? And why does this number appear so precisely in the laws that govern space, time, electricity, magnetism, and the structure of the cosmos? To answer that question, we'll travel through the history of physics. We'll visit the early astronomers who first realized light takes time to move through space. We'll explore the strange invisible fields discovered by scientists like Michael Faraday. We'll see how James Clerk Maxwell accidentally uncovered the true nature of light while studying electricity and magnetism. And along the way, we'll encounter some of the most profound ideas ever developed in science. The geometry of space-time, the strange world of quantum fields, the invisible structure of the vacuum itself. By the end of this journey, the speed of light will no longer feel like a random number. Instead, it will begin to look like something much deeper, a clue about the hidden architecture of the universe. So wherever you're listening tonight, whether it's midnight in New York, early morning in Tokyo, or somewhere quiet beneath a sky full of stars, settle in, get comfortable, and let's begin our slow exploration of the physics behind the speed of light. When physicists talk about the universe, certain numbers appear again and again. These numbers are not chosen for convenience, and they are not the result of human measurement systems. Instead, they are woven deeply into the fabric of reality. One of the most famous of these numbers is the speed of light in empty space. This speed is extraordinarily fast. Light travels at approximately 299,792,458 meters every second. That is close to 300 million meters in the time it takes to blink. If you could move at this speed, you could circle the entire Earth a little more than 7 times in a single second. It is a number so large that it is difficult to imagine directly. Yet it governs events happening constantly around us. Sunlight leaving the surface of the sun takes about 8 minutes to reach Earth. A signal sent from Earth to the moon arrives in just over 1 second. Light travelling from the nearest star beyond our sun, a star called Proxima Centauri, spends more than 4 years crossing the distance between the stars before it finally reaches our telescopes. But what makes this number truly remarkable is that it appears far beyond the study of light itself. In physics, this quantity is represented by a single letter, the letter C, and the constant C turns up in equations describing electricity, magnetism, relativity, particle physics, and cosmology. It appears in the equations that govern how atoms behave, and in the equations that describe the expansion of the universe. In other words, the speed of light is not simply a property of light, it is a property of the universe. To begin understanding why this matters, we need to step back and think about what physicists mean when they talk about a constant of nature. A constant of nature is a number that seems to be built into the laws of physics themselves. These numbers do not depend on where you perform your experiment. They do not depend on the time of day, the country you are in, or even which planet you happen to be standing on. One of the most familiar examples is the gravitational constant, which determines how strongly masses attract each other through gravity. Another is Planck's constant, which governs the strange behavior of particles and waves in quantum mechanics. And then there is the speed of light. Physicists sometimes refer to these quantities as fundamental constants because they appear in the most basic equations describing the universe. However, not all constants are equal in the way physicists think about them. Some constants depend on the units we use to measure them. Others are dimensionless numbers that remain the same no matter what measurement system is chosen. This distinction has been discussed extensively by theoretical physicist Michael Duff of Imperial College London. Duff has argued that only dimensionless constants truly reflect the deep structure of physical reality, because they do not rely on human-defined measurement systems such as meters, seconds, or kilograms. One famous dimensionless constant is called the fine structure constant. This number governs the strength of electromagnetic interactions between charged particles. It has a value of roughly 1/137, and physicists have long wondered why nature chose that particular value. The speed of light, by contrast, carries units. It tells us how far light travels in a certain amount of time. Yet despite having units, it plays a role that is every bit as fundamental as those pure numbers. In fact, the constant c acts as a bridge between two of the most basic ingredients of the universe: space and time. When Albert Einstein developed his theory of special relativity in 1905, he discovered that the speed of light connects spatial distances with time intervals in a profound way. In Einstein's framework, space and time are not separate entities but two aspects of a single structure called space-time. The speed of light serves as the conversion factor between them. This means that the constant c determines how measurements of space and measurements of time relate to each other. It tells us how far something can travel in a certain duration, but it also defines the ultimate speed limit of the universe. Nothing carrying information can move faster than light. This rule is not merely a technological limitation, it is a consequence of the structure of space-time itself. If information could travel faster than light, cause and effect would begin to break down. Events could influence other events before they had actually happened, leading to paradoxes that violate the logical structure of physical law. In this sense, the speed of light defines the boundary of causality. It separates events that can influence each other from events that cannot. Every event in the universe sits inside a region of space-time known as its light cone. Inside this region, signals travelling at or below the speed of light can connect causes and consequences. Outside this region, events remain forever disconnected. The constant c therefore does much more than describe how quickly light moves. It determines the shape of cause and effect across the entire universe. Yet even with all of this significance, one question remains surprisingly mysterious. Why does the speed of light have the value that it does? Why is it about 300 million meters per second rather than 10 times faster or 10 times slower? At first glance, this number might seem arbitrary, but many physicists suspect that it emerges from deeper features of the universe. In the 19th century, when James Clerk Maxwell developed his theory of electromagnetism, he discovered that electromagnetic waves move at a speed determined by two properties of empty space. These properties are known as electric permittivity and magnetic permeability. When Maxwell calculated the speed that electromagnetic waves should travel using these quantities, the result matched the measured speed of light. This realization led Maxwell to an extraordinary conclusion. Light itself is an electromagnetic wave. Suddenly, the speed of light was no longer just an experimental measurement. It was a quantity predicted by the underlying laws of electricity and magnetism. Later developments in physics pushed this insight even further. Quantum field theory suggests that empty space is not truly empty. Instead, it contains fluctuating fields that permeate the entire universe. Particles such as photons emerge as excitations of these fields. Within this framework, the speed of light may reflect the fundamental properties of the vacuum itself. In other words, the constant c might arise from the structure of the fields that fill the universe. This possibility has led physicists to ask even deeper questions. Could the values of physical constants be determined by the geometry of space-time? Could they emerge from hidden symmetries in the laws of physics? Or might they ultimately be connected to the conditions present at the birth of the universe? These questions remain open. For now, the speed of light stands as one of the most important clues we have about the architecture of reality. It appears in the equations of electromagnetism. It governs the structure of relativity. It connects energy and mass in Einstein's famous relation, which states energy equals mass multiplied by the speed of light squared, and it defines the ultimate speed limit for information, particles, and signals throughout the cosmos. The story of how scientists came to understand this constant is one of the most fascinating journeys in the history of physics. It begins not with modern laboratories or particle accelerators, but with careful observations of the night sky. Astronomers studying the motions of distant moons and planets were the first to discover that light does not travel instantaneously. Instead, it takes time to cross the vast distances of space. From those early discoveries, the investigation of light gradually expanded into one of the deepest explorations of nature ever undertaken. Along the way, we will encounter new ideas about electricity and magnetism, revolutionary insights into the nature of space and time, and the strange quantum fields that fill even the emptiest regions of the universe. By the end of this journey, the speed of light will no longer feel like a mysterious number appearing in equations. Instead, it will begin to look like a window into the hidden structure of reality itself. For most of human history, people did not imagine that light had a speed at all. It simply appeared to move instantly. When you light a torch, the surrounding area becomes illuminated immediately. When the sun rises over the horizon, daylight seems to flood the landscape in a single moment. There is no visible delay between the source of light and the moment it reaches your eyes. Because of this everyday experience, many early philosophers believed that light must travel infinitely fast. One of the most influential voices supporting this idea was the Greek philosopher Aristotle, who lived in the 4th century before the Common Era. Aristotle believed that light was not something that travelled through space as a moving entity. Instead, he argued that light was a kind of instantaneous presence created when luminous objects illuminated their surroundings. In Aristotle's view, light behaved less like a moving wave and more like a condition of the environment. When a source such as the sun or a flame was present, the surrounding medium simply became illuminated. This interpretation shaped thinking about light for nearly 2,000 years. It is important to remember that this belief was not unreasonable. After all, if light takes time to travel, the delay must be extremely small. Even light from the sun takes only about 8 minutes to reach Earth, and the sun is about 150 million kilometers away. At everyday distances, the delay is far too tiny for human senses to notice. If you light a candle across a room, the light reaches your eyes in a fraction of a millionth of a second. No human observer could ever perceive such a delay. For centuries, there simply was no practical way to test whether light moved instantaneously or travelled at a finite speed. The first person known to seriously question this assumption was the Italian scientist Galileo Galilei. Galileo lived during the early 17th century, a time when scientific thinking was beginning to shift toward experimentation and measurement. Instead of relying solely on philosophical reasoning, Galileo believed that nature should be investigated through careful observation and repeatable experiments. He wondered whether it might be possible to measure the speed of light directly. Galileo's idea was surprisingly simple. Imagine 2 observers standing on distant hilltops at night. Each observer holds a lantern with a shutter that can be opened or closed. One person begins by uncovering their lantern, sending a flash of light toward the second observer. As soon as the second observer sees the light, they uncover their own lantern, sending a return signal. By measuring the time between the first flash and the returning flash, Galileo hoped to detect how long light took to travel between the 2 hills. If light moved slowly enough, the delay should be measurable. Galileo and his assistants attempted versions of this experiment, placing observers at increasing distances from one another. Unfortunately, the method ran into an unavoidable limitation. Light was simply too fast. Even over distances of several kilometers, the travel time for light was far smaller than the reaction time of the observers opening their shutters. Human reflexes introduced delays far larger than the time light needed to cross the distance. Galileo concluded that if light did have a finite speed, it must be extraordinarily large. Although his experiment did not produce a measurement, it represented an important step forward. It transformed the question of light speed from a philosophical speculation into a scientific problem. The breakthrough finally arrived a few decades later, and it came from an unexpected source: the motion of a distant moon orbiting Jupiter. The astronomer responsible for this discovery was Ole Rømer, a Danish scientist working in Paris during the late 17th century. Rømer studied the movements of Jupiter's moons using telescopes at the Paris Observatory. One of these moons, called Io, provided the crucial clue. Io orbits Jupiter very rapidly, completing one full orbit in about 42 hours. As it circles the giant planet, it repeatedly passes behind Jupiter and disappears from view before emerging again on the other side. These events, known as eclipses of Io, occur at extremely regular intervals. By carefully recording the timing of these eclipses, astronomers could track Io's orbit with remarkable precision. But Romer noticed something puzzling. When Earth and Jupiter were closer together in their orbits around the Sun, the eclipses of Io appeared to occur slightly earlier than predicted. When the two planets were farther apart, the eclipses seemed to occur slightly later. At first glance, this difference might seem small, but over many observations it became unmistakable. Reaumur realized that the delays were not caused by changes in Io's orbit. Instead, they were caused by the time required for light to travel across the additional distance between Jupiter and Earth. When Earth was farther away from Jupiter, the light from Io's eclipses had to travel a longer distance to reach astronomers on Earth. This extra distance introduced a measurable delay. By analysing the timing of these eclipses, Reaumur estimated that light takes about 22 minutes to cross the diameter of Earth's orbit around the Sun. His value was not perfectly accurate by modern standards, but the conclusion was revolutionary. Light does not travel infinitely fast, it moves at a finite speed. For the first time in history, the universe had revealed that light behaves as a travelling phenomenon rather than an instantaneous effect. This discovery had profound consequences. Once scientists understood that light travels through space, the next question became obvious. What exactly is light, and how does it move? One of the earliest thinkers to propose a detailed answer was the Dutch scientist Christian Huygens. Huygens developed a theory suggesting that light behaves like a wave spreading through space, much like ripples spreading across the surface of water. According to Huygens, every point on a wavefront acts as a source of smaller wavelets, and the overall motion of light can be understood as the combined effect of these wavelets moving outward. This idea became known as Huygens' principle. The wave theory of light provided a natural explanation for many optical phenomena. Reflection, refraction, and the bending of light through lenses could all be described using wave behavior. However, the wave theory also raised a new question. Waves normally require a medium through which to travel. Water waves move through water. Sound waves travel through air. So if light is a wave, what medium carries it across the vast emptiness of space? Many scientists believed that space must be filled with an invisible substance known as the luminiferous ether. This hypothetical medium would act as the carrier for light waves, allowing them to propagate through the vacuum between planets and stars. The ether concept would dominate scientific thinking for centuries, even though it would eventually be abandoned. What matters most about this period in the history of physics is that light had begun to reveal its true nature. Astronomical observations had shown that light travels at a finite speed. Experimental thinking had transformed light into a measurable phenomenon, and theoretical ideas from scientists like Christian Huygens had introduced the possibility that light might be a wave moving through space. These developments mark the birth of a new scientific field, the systematic study of light, known as optics. Over the following centuries, researchers would refine these ideas through increasingly sophisticated experiments. They would measure the speed of light with greater accuracy, uncover its wave properties in detail, and eventually discover its deep connection to electricity and magnetism. But the first crucial step had already been taken. Humanity had learned that light is not instantaneous. It moves, and its journey through space takes time. Once scientists accepted that light travels at a finite speed, attention naturally turned to a deeper question. What exactly is light? During the 17th and 18th centuries, two competing ideas began to take shape. One view suggested that light consisted of tiny particles emitted by luminous objects. This idea was supported by the great physicist Isaac Newton, whose reputation carried enormous influence. Newton's particle theory, often called the corpuscular theory of light, explained certain phenomena quite well. It could describe how light travels in straight lines and how it reflects from mirrors. Because of Newton's authority, the particle picture remained widely accepted for many decades, yet another possibility continued to quietly gather support. Perhaps light behaves not like a stream of particles, but like a wave. Waves are familiar from everyday life. When a stone is dropped into a still pond, circular ripples spread outward across the surface. Sound travels as waves of pressure through air. Ocean swells carry energy across vast distances through moving water. If light were a wave, then it might display behaviour similar to these other forms of wave motion. The decisive evidence arrived in the early 19th century through the work of an English physicist named Thomas Young. In the year 1801, Young performed one of the most elegant experiments in the history of physics. The setup was deceptively simple. He allowed light from a single source to pass through two very narrow openings placed close together. These openings are now known as slits. After passing through the slits, the light spread outward and fell onto a screen behind them. If light behaved as a stream of particles travelling in straight lines, the screen would display two bright bands corresponding to the two slits. But that is not what appeared. Instead, the screen displayed a series of alternating bright and dark stripes stretching across the surface. These stripes formed a pattern known as an interference pattern. The explanation lies in the behaviour of waves. When two waves meet, they interact with each other. If the peaks of one wave align with the peaks of another, they reinforce one another and produce a stronger wave. This effect is called constructive interference. If the peak of one wave meets the trough of another, they cancel each other out. This produces destructive interference. Young's two slits acted as sources of light waves that spread outward and overlapped. In some regions, the waves reinforced each other, producing bright bands. In other regions, they cancelled each other, producing dark bands. This pattern could only be explained if light behaved as a wave. The double-slit experiment became one of the most powerful demonstrations in all of physics, and it continues to be studied in laboratories even today. It revealed that light possesses a property called interference, which is characteristic of wave behaviour, but the story did not end there. A French physicist named Augustin-Jean Fresnel soon expanded the wave theory with remarkable mathematical insight. Working in the early 1800s, Fresnel developed detailed equations describing how waves spread, bend, and interact. One of the key phenomena Fresnel investigated was diffraction. Diffraction occurs when waves encounter an obstacle or pass through a narrow opening. Instead of continuing in straight lines, the waves spread outward. This effect can easily be seen in water waves approaching a gap in a barrier, where the ripples fan out beyond the opening. Light behaves in the same way. When light passes through a small aperture or moves around the edge of an object, it spreads slightly into regions that would otherwise remain dark. Fresnel's mathematical analysis showed that these diffraction patterns matched the predictions of wave theory with remarkable accuracy. His work was so convincing that the wave model of light rapidly gained acceptance among scientists across Europe. By the middle of the 19th century, the wave theory of light had become the dominant explanation within the scientific community. Yet this success created a new puzzle. All known waves required a medium through which to travel. Sound waves move through air or water. Ocean waves move through liquid water. Even vibrations along a guitar string require the string itself to carry the motion. If light is a wave, then what exactly is waving? This question led scientists to propose the existence of a mysterious substance known as the luminiferous ether. The word luminiferous means light-bearing, and the ether was imagined as a medium filling all of space. According to this idea, the ether permeated the entire universe, passing effortlessly through planets, stars, and empty space alike. Light waves were thought to travel through this invisible medium in the same way that sound waves move through air. The ether was assumed to be incredibly strange. It had to be rigid enough to support the extremely rapid oscillations of light waves, yet at the same time it needed to offer no resistance to the motion of planets moving through space. Physicists imagined it as a substance that filled the cosmos while remaining completely undetectable. Although this idea might sound unusual today, it seemed entirely reasonable at the time. After all, waves without a medium appeared impossible according to the scientific knowledge of the era. For several decades, the ether became a central feature of optical physics. Researchers continued refining the wave theory of light while assuming that the ether served as its invisible carrier. Experiments were designed to detect the motion of Earth through this cosmic medium, much as a moving ship experiences wind as it travels across the ocean. Meanwhile, the mathematical description of light grew increasingly sophisticated. Scientists developed precise equations describing reflection, refraction, interference, and diffraction. Optical instruments such as telescopes and microscopes were improved through a deeper understanding of how light waves behave when passing through lenses. The field of optics was rapidly transforming into a precise and predictive science. yet another transformation was quietly approaching. During the same period, scientists were uncovering unexpected connections between electricity and magnetism. Experiments by researchers such as Hans Christian Ørsted and Michael Faraday were revealing that electric currents could produce magnetic fields and that changing magnetic fields could generate electric currents. These discoveries hinted that electricity and magnetism might be two aspects of a single unified phenomenon. Eventually, these ideas would merge with the wave theory of light in a way that no one had anticipated. And when that happened, light would reveal an even deeper secret about the structure of the universe. During the early 19th century, scientists studying light were not the only ones uncovering surprising phenomena. In laboratories across Europe, another set of discoveries was quietly reshaping the understanding of nature. These discoveries involved two seemingly separate forces, electricity and magnetism. Electricity had already become familiar through experiments with charged objects, sparks, and batteries. Magnetism was known through the behavior of lodestones and compass needles. At first glance, these forces appeared to belong to entirely different realms. But nature had a habit of revealing unexpected connections. One of the most important moments arrived in the year 1820, thanks to the work of a Danish physicist named Hans Christian Ørsted. Ørsted had long suspected that electricity and magnetism might be related, though the connection remained unclear. During one of his lectures at the University of Copenhagen, Ørsted performed an experiment that would change physics forever. He passed an electric current through a wire while a compass needle sat nearby. A compass normally points toward the magnetic north of Earth, guided by the planet's magnetic field. But when Ørsted allowed the electric current to flow through the wire, the compass needle suddenly shifted its direction. The needle had responded to the electric current. This observation revealed something remarkable. A moving electric charge creates a magnetic influence around it. Electricity could produce magnetism. At first, the effect might seem modest, a small twitch of a compass needle. Yet this single observation hinted at a deep relationship between two fundamental forces. News of Ørsted's discovery spread rapidly across Europe. Scientists began exploring the phenomenon with intense curiosity. Among the most influential of these researchers was the French physicist André-Marie Ampère. Ampère quickly recognized that Ørsted's discovery pointed toward a broader theory. Through careful experiments, Ampère demonstrated that electric currents exert forces on each other. Two wires carrying electric currents can attract or repel one another depending on the direction of the current flowing through them. Ampère developed mathematical descriptions of these interactions, laying the foundation for what would later be called electrodynamics. His work showed that magnetism could be understood as a consequence of moving electric charges. In other words, magnetism was not a separate force after all. It was deeply connected to electricity. While Ampère approached the problem with mathematical precision, another scientist explored the phenomenon from a very different perspective. Michael Faraday, working in England, brought an extraordinary experimental intuition to the study of electricity and magnetism. Faraday had little formal mathematical training, yet his physical insight was exceptional. Through hundreds of experiments, he investigated how electric currents, magnetic fields, and changing magnetic environments interact with one another. One of Faraday's most important discoveries involved electromagnetic induction. Faraday showed that a changing magnetic field can produce an electric current in a nearby conductor. If a magnet is moved through a coil of wire, an electric current appears in the wire. If the magnet stops moving, the current disappears. This effect revealed that electricity and magnetism could influence each other dynamically. Electric currents could create magnetic effects, and changing magnetic fields could generate electricity. But Faraday introduced something even more profound than this observation. He proposed that forces such as electricity and magnetism do not act across empty space in an instantaneous leap. Instead, they operate through invisible structures that fill the surrounding region. Faraday called these structures fields. To visualize these fields, Faraday introduced the idea of field lines. Imagine sprinkling iron filings around a magnet. The tiny filings arrange themselves in curved patterns that trace the shape of the magnetic influence surrounding the magnet. These patterns reveal the structure of the magnetic field. Faraday suggested that the field itself is a real physical entity extending through space. Objects do not influence each other by reaching across empty space directly. Instead, they interact through the field surrounding them. This idea represented a dramatic shift in scientific thinking. Earlier theories had often relied on mechanical models. Forces were imagined as the result of tiny particles pushing or pulling one another through contact. Faraday's concept of fields replaced that picture with something more abstract but far more powerful. Electric and magnetic influences were no longer confined to objects themselves. They filled the space around those objects. The universe, according to Faraday's vision, was threaded with invisible structures carrying energy and influence from place to place. Although Faraday's field concept initially faced skepticism, its explanatory power soon became undeniable. One particularly important insight involved the way energy moves through electromagnetic systems. In the late 19th century, the English physicist John Henry Poynting studied how electromagnetic energy flows through space. Poynting developed a mathematical description showing that energy moves through electromagnetic fields in a specific direction. This concept is known today as the Poynting vector. In words, the idea can be expressed as a principle, stating that the flow of electromagnetic energy at any point in space depends on the interaction between electric fields and magnetic fields in that region. When electric and magnetic fields interact, they carry energy through space together. This realization was remarkable because it showed that electromagnetic energy does not simply travel along wires or inside physical objects. Instead, it flows through the surrounding fields themselves. Energy could move through space even when no material substance appeared to carry it. The implications of this field-based picture were profound. For centuries, scientists had tried to understand physical phenomena by imagining tiny mechanical parts pushing and pulling one another like gears in a clock. But the emerging science of electricity and magnetism suggested something very different. Nature might not be built entirely from mechanical pieces interacting through contact. Instead, it might be structured around fields that fill space and transmit forces continuously. Electric fields, magnetic fields, and the energy carried within them were becoming central characters in the story of physics. And this story was about to intersect with the mystery of light. For many years, the study of optics and the study of electricity had developed along separate paths. Researchers studying lenses, reflection, and interference did not initially suspect that their work might connect with the phenomena of electric currents and magnetic fields. Yet the pieces were quietly falling into place. The wave theory of light had already shown that light behaves like a wave spreading through space. At the same time, the discoveries of Ørsted, Ampere, and Faraday had revealed that electric and magnetic influences propagate through invisible fields. Two different branches of physics were describing waves and fields moving through space. Soon, a brilliant Scottish physicist would recognise that these ideas were not separate at all. They were parts of the same phenomenon, and when those pieces were finally assembled, light itself would be revealed as something even more extraordinary than anyone had imagined. In the middle of the 19th century, a young Scottish physicist began assembling pieces of a puzzle that had been scattered across decades of experiments. His name was James Clerk Maxwell. Maxwell possessed an unusual combination of talents. He had a deep physical intuition like Michael Faraday, and at the same time he had extraordinary mathematical skill. Where Faraday had imagined fields as lines of influence stretching through space, Maxwell sought to translate those ideas into precise mathematical language. At the time, electricity and magnetism were known to be connected. Scientists understood that electric currents could create magnetic effects, and that changing magnetic conditions could generate electrical currents. These discoveries had emerged from the work of Hans Christian Ørsted, André-Marie Ampère, and Michael Faraday. But the underlying principles tying all of these effects together had not yet been fully expressed. Maxwell began carefully analysing Faraday's concept of fields. Rather than thinking of electricity and magnetism as forces acting at a distance, Maxwell treated the electric field and the magnetic field as physical quantities that existed at every point in space. These fields could change over time, interact with one another, and carry energy. Maxwell then expressed these relationships through a set of mathematical equations that described how electric and magnetic fields behave. Today, these relations are known collectively as Maxwell's equations. They describe four fundamental principles governing electromagnetism. One equation explains how electric charges produce electric fields. Another describes how magnetic fields arise from moving electric charges. A third shows how changing magnetic fields generate electric fields. And a fourth explains how electric currents and changing electric fields create magnetic fields. Together, these equations reveal that electricity and magnetism are not separate forces at all. They are two aspects of a single unified phenomenon called electromagnetism. But Maxwell noticed something even more remarkable hidden within his equations. If an electric field changes over time, it produces a magnetic field. If a magnetic field changes over time, it produces an electric field. In other words, each field can generate the other. Maxwell realized that this mutual relationship allows something extraordinary to happen. A changing electric field can create a magnetic field, which then creates another electric field, which creates another magnetic field, and so on. This process can continue indefinitely. In effect, the electric and magnetic fields sustain each other as they move through space. Maxwell had discovered the possibility of self-propagating electromagnetic waves. Unlike waves in water or sound waves in air, these waves did not require a material medium to carry them. The electric and magnetic fields themselves were enough to sustain the motion. When Maxwell analyzed the mathematics describing these waves, he found that they should travel at a specific speed determined by two fundamental properties of space. These properties are known as electric permittivity and magnetic permeability. Electric permittivity describes how easily an electric field can form in a region of space. Magnetic permeability describes how readily magnetic fields can exist in that same region. When Maxwell combined these properties in his equations, he derived a relationship that predicted the speed of electromagnetic waves. The relationship can be stated clearly in words. The speed of electromagnetic waves equals 1 divided by the square root of electric permittivity multiplied by magnetic permeability. Maxwell then calculated the numerical value of this speed, using the best measurements available at the time. The result was astonishing. The predicted speed of electromagnetic waves matched the measured speed of light. The agreement was not approximate, it was strikingly close. Maxwell immediately recognized the significance of this discovery. Light itself must be an electromagnetic wave. In one elegant insight, the fields studied by Faraday and the waves studied by optical physicists were revealed to be the same phenomenon. Light was not simply a mysterious radiation emitted by luminous objects. It was a ripple in the electromagnetic field. This realization transformed the understanding of light. It also answered a long-standing question about the wave theory of light. Earlier scientists had believed that waves must travel through a medium such as the luminiferous ether. Maxwell's equations showed that electromagnetic waves could propagate through empty space without any supporting substance. The electric and magnetic fields themselves were enough to carry the wave forward. Maxwell's work was revolutionary, but his original formulation of the equations was not especially easy to read. His mathematical descriptions were complex and expressed using methods that were common at the time but unfamiliar to later generations. Several decades later, an English physicist named Oliver Heaviside revisited Maxwell's work. Heaviside possessed a remarkable ability to simplify complicated mathematical ideas. By reorganizing Maxwell's equations and expressing them using a new mathematical language called vector analysis, Heaviside reduced the original lengthy formulations to the 4 concise equations used in physics today. These simplified equations made Maxwell's theory far easier to understand and apply. Engineers, physicists, and mathematicians could now explore electromagnetic phenomena with greater clarity. Yet despite the elegance of the theory, one crucial question remained. Did electromagnetic waves actually exist in nature? Maxwell's equations predicted them, but at the time no one had directly observed such waves outside the visible light spectrum. The answer arrived in the late 1800s through the work of a German physicist named Heinrich Hertz. Hertz set out to test Maxwell's predictions experimentally. In his laboratory, he built a device capable of producing rapidly oscillating electric currents. When these currents flowed through a small gap between metal conductors, they generated bursts of electromagnetic radiation. Hertz placed a loop of wire some distance away from the transmitter. When electromagnetic waves from the transmitter reached the loop, they induced tiny electrical sparks in the receiving circuit. These sparks confirmed that energy had traveled through space between the two devices. Hertz had created and detected electromagnetic waves in the laboratory. Even more impressive, Hertz demonstrated that these waves displayed the same behaviors as visible light. They could reflect from metal surfaces, bend around obstacles, and form interference patterns. In other words, they behaved exactly like light waves predicted by Maxwell's theory. Hertz himself famously remarked that the experiments proved the existence of Maxwell's electromagnetic waves. Though he believed they might never have practical applications, history would prove otherwise. The electromagnetic waves Hertz produced in his laboratory were radio waves, the same kind that now carry radio broadcasts, television signals, mobile phone communications, and wireless internet across the world. But the deeper significance of Hertz's experiments was conceptual rather than technological. They confirmed that light belongs to a vast family of electromagnetic radiation. Visible light represents only a small portion of a much broader electromagnetic spectrum that includes radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. All of these forms of radiation are electromagnetic waves traveling through space at the same fundamental speed. Maxwell's equations had done something extraordinary. They had revealed that electricity, magnetism, and light were all manifestations of the same underlying field, and hidden within that field was a constant that would soon become one of the most important numbers in all of physics. The speed of light was no longer merely a measured quantity. It had become a prediction of the fundamental laws of nature. When James Clerk Maxwell finished developing his theory of electromagnetism in the 1860s, he had not merely explained electricity and magnetism. He had uncovered something far deeper. Hidden inside his equations was the reason light travels at the speed it does. Before Maxwell's work, the speed of light had been treated as a measured quantity. Astronomers like Ulrömer had estimated it through observations of Jupiter's moon, Io. Later experiments using rotating mirrors and long laboratory paths refined the measurement further. But these experiments told scientists only what the speed of light was. They did not explain why it had that value. Maxwell's theory provided the missing piece. His equations showed that electromagnetic waves propagate through space at a speed determined by two measurable properties of the vacuum. These properties are known as electric permittivity and magnetic permeability. Electric permittivity describes how strongly electric fields respond to electric charges in a region of space. Magnetic permeability describes how magnetic fields arise and interact with moving electric charges. Although these quantities might sound abstract, they are real measurable features of nature. Physicists can determine their values through carefully designed experiments involving electric charges, magnetic fields, and electrical currents. Maxwell discovered that when these two properties are combined mathematically, they produce a specific propagation speed for electromagnetic waves. The relationship can be stated clearly in words. The speed of electromagnetic waves equals 1 divided by the square root of electric permittivity multiplied by magnetic permeability. When Maxwell inserted the known values of these two constants into this relationship, the result came out astonishingly close to the measured speed of light. In other words, the speed of light was not an independent property of light itself. It was determined by the electromagnetic properties of space. This realization was profound. It suggested that the speed of light emerges from the structure of the vacuum. Space itself contains measurable characteristics that determine how electric and magnetic fields behave. When these fields interact and oscillate together, they form electromagnetic waves that move at a specific speed set by the properties of space. Light travels at its particular speed because space allows electric and magnetic fields to interact in that precise way. This insight dramatically changed how physicists thought about the vacuum. For centuries, empty space had been imagined as a passive void, an absence of matter where nothing happens. But Maxwell's theory revealed something quite different. Even in the absence of particles, space possesses physical properties that can be measured and described mathematically. Electric fields can exist in empty space. Magnetic fields can exist in empty space. And these fields can carry energy and momentum as they propagate. In this sense, the vacuum behaves almost like a physical medium. The comparison is not perfect, but it can be helpful. Just as water supports the motion of waves on the surface of the ocean, the electromagnetic properties of space allow electric and magnetic fields to form waves that move through the vacuum. However, unlike water or air, this medium does not consist of molecules or atoms. It is not a substance that can be stirred or compressed. Instead, it is a property of space itself. This idea began to blur the distinction between emptiness and substance. The vacuum was no longer simply nothing. It had structure, it had measurable constants, and it could support the propagation of waves carrying energy across vast distances. The philosophical implications of this realization were enormous. For the first time, the behavior of light could be traced back to the fundamental characteristics of space itself. The universe was not merely a collection of objects interacting through forces. it was also shaped by the properties of the space between those objects. In the late 19th century, this insight inspired both excitement and confusion. Scientists wondered what exactly gave space its electromagnetic properties. Some continued to believe that a hidden medium called the luminiferous ether must fill the universe, providing the substance that allowed electromagnetic waves to propagate. Others suspected that fields themselves might be more fundamental than any underlying material. These debates continued for decades. What remained clear was that the speed of light had become deeply embedded in the laws of physics. It was no longer just the speed of visible light waves. It was the natural speed at which disturbances in the electromagnetic field travel through space. This meant that the same speed applies to radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays. All of these forms of radiation belong to the electromagnetic spectrum. Although they differ dramatically in wavelength and frequency, they all propagate through empty space at the same fundamental speed. The discovery raised another intriguing possibility. If the speed of light arises from the properties of space, then perhaps it is not simply the speed of light. Perhaps it is the speed at which any massless disturbance travels through space-time. Later developments in physics would confirm this suspicion. In modern theories, particles that possess no rest mass must travel at this same universal speed. Photons, which carry electromagnetic radiation, move at this speed. Gravitational waves, predicted by Einstein's theory of general relativity and detected by the Laser Interferometer Gravitational Wave Observatory in the year 2015, also travel at essentially the same speed. The constant that Maxwell uncovered turned out to be far more universal than anyone had imagined. But there was still a puzzle that troubled physicists toward the end of the 19th century. If electromagnetic waves move through space with a specific speed determined by the properties of the vacuum, then relative to what frame of reference is that speed measured? After all, ordinary waves move at a particular speed relative to the medium that carries them. Sound waves travel through air at roughly 340 meters per second relative to the air itself. Water waves travel across the surface of water relative to the water. If electromagnetic waves are similar, then they should travel at a specific speed relative to whatever medium supports them. This reasoning seemed to strengthen the case for the existence of the luminiferous ether. If the ether filled all of space, then electromagnetic waves would travel at their characteristic speed relative to that medium. Observers moving through the ether should detect variations in the speed of light depending on their direction of motion. But when scientists attempted to measure this effect, the results became increasingly puzzling. Experiments designed to detect Earth's motion through the ether failed to find any difference in the speed of light in different directions. Light appeared to travel at exactly the same speed, regardless of the motion of the observer. This strange result would eventually lead to one of the most revolutionary developments in the history of physics. A young physicist working at the Swiss Patent Office would propose that the constancy of the speed of light was not a problem to be explained away. It was a fundamental feature of the universe, and accepting that idea would transform our understanding of space and time themselves. By the late 19th century, the wave theory of light had achieved remarkable success. Experiments involving interference, diffraction, and reflection all supported the idea that light behaves as a wave. Maxwell's equations had gone even further, revealing that light was an electromagnetic wave produced by oscillating electric and magnetic fields. Yet a troubling question remained. If light is a wave, then what exactly is waving? Every known wave in nature required a medium. Sound waves move through air. Ocean waves travel through water. Vibrations along a guitar string require the string itself. Even the ripples spreading across the surface of a pond need the water beneath them to carry the motion. So it seemed natural to assume that light must also travel through some kind of medium. Physicists proposed that all of space was filled with a subtle and invisible substance known as the luminiferous ether. The term luminiferous means light-bearing, and the ether was imagined as the medium that carried electromagnetic waves across the universe. This ether would have to possess unusual properties. It needed to be extremely rigid in order to support the incredibly rapid oscillations of light waves, which vibrate hundreds of trillions of times every second. At the same time, it had to offer no resistance to the motion of planets, moons, and stars passing through it. Earth, for example, moves around the Sun at roughly 30 kilometers per second. If the ether filled all of space, then Earth should constantly be moving through it. This motion would produce an effect similar to wind. Imagine riding a bicycle on a calm day. Even if the air itself is still, your motion through it creates a breeze against your face. The faster you move, the stronger the wind feels. Physicists reasoned that Earth's motion through the ether should produce something similar. As Earth travelled through the ether, light moving in the direction of Earth's motion might travel slightly faster or slower relative to observers on Earth. This hypothetical effect became known as the ether wind. Detecting this ether wind would provide clear evidence that the ether existed and that light travelled through it. The challenge was to measure the speed of light with enough precision to detect the difference. In the 1880s, two American physicists set out to perform this test. Their names were Albert Abraham Michelson and Edward Williams Morley. Michelson had already established a reputation as one of the most skilled experimental physicists of his time. He specialized in extremely precise measurements using optical instruments. Together with Morley, he designed an experiment based on a technique called interferometry. Interferometry takes advantage of the wave nature of light. When two beams of light meet, their waves combine to produce interference patterns. These patterns can shift if one beam travels a slightly different distance or experiences a small change in speed. Michelson's interferometer split a beam of light into two separate paths arranged at right angles to one another. One beam travelled in the direction of Earth's motion through the ether, while the other travelled perpendicular to that motion. After reflecting from mirrors, the two beams recombined to produce an interference pattern. If Earth were moving through the ether, the speed of light along the two paths should differ slightly. The beam travelling into the ether wind would move differently than the beam travelling across it. This difference would change the interference pattern in a measurable way. Michelson and Morley constructed their apparatus with extraordinary care. The entire device was mounted on a massive stone slab floating in a pool of mercury. This arrangement allowed the instrument to rotate smoothly, letting the researchers measure light travelling in different directions. By rotating the apparatus, they could detect changes in the interference pattern as the orientation shifted relative to Earth's motion through space. The experiment was carried out in the year 1887 at the Case School of Applied Science in Cleveland, Ohio. The expected result seemed straightforward. If the ether existed, then rotating the interferometer should reveal a shift in the interference pattern as the apparatus changed direction relative to the ether wind. But when Michelson and Morley carefully analysed their results, they encountered something deeply puzzling. There was no detectable shift. No matter how they oriented the instrument, the interference pattern remained unchanged. Light appeared to travel at exactly the same speed in every direction. The ether wind could not be detected. The result is now known as the Michelson-Morley null result, and it became one of the most famous outcomes in the history of physics. At first, scientists were reluctant to abandon the ether hypothesis. The concept had become deeply embedded in scientific thinking, and many believed the experiment must be missing something. Various explanations were proposed. One idea suggested that objects moving through the ether might physically contract in the direction of motion. This hypothesis, developed by George Fitzgerald and Hendrik Lorentz, proposed that the lengths of objects change just enough to hide the effects of the ether wind. Another suggestion involved subtle changes in time measurement that might compensate for the motion through the ether. Although these proposals could mathematically explain the null result, they felt somewhat artificial. They seemed to introduce new assumptions simply to preserve the idea of the ether. The deeper problem remained unresolved. Maxwell's theory predicted that electromagnetic waves travel at a fixed speed determined by the properties of space. Yet if space were filled with a medium like the ether, observers moving through that medium should measure different speeds depending on their motion. But experiments consistently failed to detect such differences. Light behaved as though its speed were the same in every direction and for every observer. This contradiction between theory and observation created a growing sense of unease among physicists. The laws of electromagnetism seemed to suggest one thing, while the classical ideas about motion suggested another. For several decades, this tension lingered without a satisfying resolution. Then, in the early years of the 20th century, a young physicist named Albert Einstein approached the problem from an entirely new perspective. Instead of trying to explain why the speed of light appeared constant, Einstein proposed that the constancy of the speed of light should be taken as a fundamental principle of nature. Accepting that idea would require a radical revision of how space and time themselves were understood. And once those revisions were made, the ether would quietly disappear from physics altogether. At the beginning of the 20th century, physics stood at an uncomfortable crossroads. On one hand, Maxwell's theory of electromagnetism had been spectacularly successful. It explained light, electricity, and magnetism with a single elegant framework. On the other hand, experiments searching for the luminiferous ether had repeatedly failed to detect any trace of it. The Michelson-Morley experiment had shown that light seemed to travel at exactly the same speed in every direction, regardless of Earth's motion through space. This result was deeply puzzling. According to the traditional ideas of motion inherited from Isaac Newton, speed should add together in simple ways. If a train moves forward and someone on the train throws a ball ahead, the speed of the ball relative to the ground equals the speed of the train plus the speed of the throw. This simple rule had worked perfectly for everyday motion. But light refused to behave that way. No matter how scientists tried to measure it, the speed of light remained the same. Whether the observer moved toward the light source or away from it, the measured speed did not change. Something fundamental about motion itself seemed to be misunderstood. In the year 1905, a young physicist working in the Swiss Patent Office in Bern proposed a radical solution to this puzzle. His name was Albert Einstein. Einstein's paper, titled On the Electrodynamics of Moving Bodies, introduced a new framework for understanding motion and the laws of physics. This framework became known as the theory of special relativity. Rather than trying to explain the strange results of experiments by modifying existing theories, Einstein began with two simple principles. The first principle stated that the laws of physics are the same in every inertial reference frame. An inertial reference frame is any frame of motion that moves at constant velocity without acceleration. This means that the fundamental laws governing nature do not depend on whether an observer is at rest or moving steadily through space. The second principle was even more striking. Einstein proposed that the speed of light in empty space is the same for all observers, regardless of the motion of the light source or the observer. In other words, the speed of light is constant. This principle might seem almost obvious today, but at the time it contradicted the expectations of classical mechanics. According to Newtonian thinking, velocities should combine, yet Einstein's second postulate insisted that the speed of light remains unchanged no matter how observers move relative to one another. At first glance, this idea appears impossible. Imagine two spacecraft moving toward each other at extremely high speed. If each spacecraft shines a beam of light toward the other, common intuition suggests that each observer should measure the light approaching faster than the usual speed of light. But Einstein's theory states that both observers still measure the same speed. The only way this can happen is if something else changes. Einstein realized that space and time themselves must adjust in order to preserve the constant speed of light. This was the revolutionary insight. Space and time are not fixed, absolute backgrounds in which events unfold. Instead, they are flexible quantities that depend on the motion of the observer. Distances can change, time intervals can change. Even the order of events can appear different depending on the observer's state of motion. These effects are not illusions or measurement errors. They are real physical consequences of the structure of space-time. Although Einstein's work introduced the theory in its final form, the mathematical groundwork had already been developed by several earlier scientists. One of these was the Dutch physicist Hendrik Lorentz. Lorentz had been studying how electromagnetic equations behave when observers move relative to one another. To make Maxwell's equations consistent with the results of experiments like Michelson and Morley, Lorentz introduced mathematical transformations describing how measurements of space and time change between moving frames. These relations became known as the Lorentz transformations. They describe how time intervals and spatial distances transform when observers move at constant velocity relative to one another. The Lorentz transformations contain several remarkable consequences. One is time dilation. This effect means that moving clocks tick more slowly relative to stationary observers. Another consequence is length contraction. Objects moving at high speed appear slightly shorter along the direction of motion. These effects are normally far too small to notice in everyday life, because they become significant only when speeds approach the speed of light. But at extremely high velocities, the changes become dramatic. Another important figure contributing to the development of relativity was the French mathematician and physicist Henri Poincaré. Poincaré recognized that Lorentz's transformations formed a consistent mathematical framework and that they reflected a deeper symmetry in the laws of nature. He also emphasized the importance of the principle of relativity, the idea that the laws of physics must look the same in all inertial reference frames. Einstein's genius was to recognize that these ideas were not merely mathematical tools. They described the true structure of space and time. By accepting the constancy of the speed of light as a fundamental principle, Einstein eliminated the need for the luminiferous ether altogether. If the speed of light is the same for every observer, then there is no preferred frame of reference relative to which light travels. There is no hidden medium defining absolute rest. The ether quietly disappears from the theory. Instead of light waves moving through a substance filling space, electromagnetic waves propagate through space-time itself. This shift marked one of the most profound conceptual revolutions in the history of science. In classical physics, space and time were viewed as absolute and independent. Time flowed uniformly everywhere in the universe, and space provided a rigid stage on which events occurred. Einstein's theory replaced this picture with something far more subtle. Space and time became intertwined aspects of a single four-dimensional structure known as space-time. Within this structure, the speed of light plays a special role. It acts as a universal conversion factor, linking spatial distance and temporal duration. It also defines the ultimate speed limit for the transmission of information and energy. The invariance of the speed of light means that every observer, regardless of their motion, measures the same value for this speed. This property is known as space-time invariance. It means that the fundamental laws governing nature remain consistent across all inertial frames of reference. Experiments over the past century have confirmed these predictions with extraordinary precision. Particles accelerated to enormous speeds in facilities such as the Large Hadron Collider at the European Organization for Nuclear Research behave exactly as relativity predicts. Atomic clocks carried aboard high-speed aircraft tick at slightly different rates compared with clocks on the ground, confirming the phenomenon of time dilation. Even the satellites in the Global Positioning System must account for relativistic effects to maintain accurate timing signals. What began as an attempt to understand the speed of light ultimately reshaped our understanding of the universe. The constant c was no longer simply the speed of electromagnetic waves. It had become a fundamental feature of spacetime itself. And once scientists began to explore the geometry of spacetime more deeply, they discovered that this constant also determines the boundaries of cause and effect throughout the cosmos. Albert Einstein's theory of special relativity introduced a radical idea. Space and time are not separate entities. Instead, they form a single interconnected structure. Yet the full geometric meaning of this idea did not become clear until a mathematician and physicist named Hermann Minkowski provided a new way to visualize it. Minkowski had once been Einstein's professor in Zurich, and he was deeply interested in the mathematical structure underlying physical laws. In the year 1908, only a few years after Einstein published his theory of special relativity, Minkowski proposed a powerful reinterpretation. According to Minkowski, space and time should be treated as parts of a unified four-dimensional framework known as space-time. In everyday life, we describe locations using 3 dimensions of space. A point in space can be specified by giving 3 coordinates, one describing position from left to right, another describing position forward and backward, and a third describing position up and down. But events in the universe require more than just spatial coordinates. Every event also occurs at a specific moment in time. Minkowski's insight was to combine these 3 spatial dimensions with the dimension of time into a single 4-dimensional structure. In this picture, every event in the universe has 4 coordinates, 3 describing where it occurs and 1 describing when it occurs. An event might be the flash of a camera, the explosion of a star, or a photon striking a detector in a laboratory. Space-time becomes the stage on which every physical process unfolds. What makes this idea especially interesting is the role played by the speed of light. The constant speed of light links distances in space with intervals of time. In fact, the speed of light acts as a conversion factor between these 2 kinds of measurement. A distance travelled by light in 1 second corresponds to roughly 300 million meters. This relationship means that time and space can be expressed in comparable units when studying space-time geometry. In Minkowski's formulation, the geometry of space-time determines how events relate to one another. The constant speed of light plays a central role in defining that geometry. One of the most important concepts arising from this picture is the idea of the light cone. To understand a light cone, imagine a single event occurring at a specific location and moment. perhaps a flash of light is emitted from a lamp. From that instant, the light spreads outward in all directions at the speed of light. As time passes, the expanding sphere of light grows larger and larger. If we represent this expanding sphere within space-time, it forms a shape resembling a cone. The light moving forward in time creates what is called the future light cone. The paths that light could have taken to reach the event form the past light cone. These cones define the boundaries of causal influence. Any event inside the future light cone can be affected by the original event. For example, if a light bulb flashes in a room, signals from that flash can reach objects nearby after a short delay. Those objects lie inside the future light cone of the flash. Events outside this cone cannot be influenced by the flash, because signals travelling at or below the speed of light cannot reach them in time. Similarly, the past light cone contains all events that could have influenced the original event. If a photon strikes a telescope on Earth, the telescope's detection lies within the future light cone of whatever cosmic event produced that photon. This geometric structure divides space-time into three regions. The first region contains events inside the future light cone. These events can be influenced by the original event. The second region contains events inside the past light cone. These events could have influenced the original event. The third region contains events outside both cones. These events are separated by space-time intervals that prevent any signal travelling at or below the speed of light from connecting them. Physicists call this region space-like separation. In this region, cause and effect cannot operate. The concept of light cones reveals something profound about the structure of the universe. The speed of light determines the boundaries within which causal relationships can occur. No signal, no influence, and no transfer of information can travel faster than light. Because of this universal limit, cause always precedes effect in every frame of reference. The geometry of space-time protects the logical structure of physical law. As scientists continued exploring relativity throughout the 20th century, the geometric approach to space-time became increasingly important. One of the physicists who developed these ideas further was the British mathematician and physicist Roger Penrose. Penrose introduced powerful geometric tools for studying the structure of space-time on both cosmic and microscopic scales. Among his contributions was a method of visualizing space-time relationships called a Penrose diagram. A Penrose diagram compresses the enormous distances and timescales of the universe into a manageable geometric representation. By carefully transforming the coordinates used to describe space-time, the diagram brings infinitely distant regions into a finite picture. This technique allows physicists to visualize how light rays move through space-time and how different regions of the universe connect causally. Penrose diagrams are especially useful for studying extreme environments such as black holes and the expanding universe. In these diagrams, the paths followed by light always appear as straight lines angled at 45 degrees. This feature reflects the fact that light travels at the same fundamental speed in every direction. Anything moving slower than light must follow a path that stays within the boundaries defined by these lines. Through this geometric perspective, the role of the speed of light becomes even clearer. It is not merely the speed of electromagnetic waves. It is the speed that defines the structure of space-time itself. Every event in the universe sits within a network of light cones that determine which other events it can influence and which events can influence it. The constant speed of light shapes the causal architecture of the cosmos. Even the most distant galaxies obey this rule. Light travelling from those galaxies may take millions or billions of years to reach Earth, but the path of that light still follows the boundaries defined by space-time geometry. The universe unfolds according to these constraints. Nothing can outrun the expanding sphere of influence defined by the speed of light. Understanding space-time in this geometric way transformed relativity from a collection of equations into a deeper description of reality. Space and time are not passive backgrounds. They form an active structure that governs how events unfold and how signals propagate. And at the heart of that structure lies a constant that began as a measurement of how quickly light travels through empty space. The speed of light has become something far more fundamental. It is the boundary between what can happen and what cannot. When Albert Einstein proposed that the speed of light remains constant for all observers, he introduced a principle that seems almost simple when first stated. Yet that single principle carries consequences that reshape how motion, time, and distance behave in the universe. The key insight is that if every observer measures light travelling at the same speed, then something else must adjust whenever objects move relative to one another. That something is space and time themselves. To understand how this works, physicists often imagine a device known as a light clock. A light clock is conceptually simple. Picture two perfectly aligned mirrors facing one another. A pulse of light bounces between them, reflecting back and forth. Each time the light completes a round trip between the mirrors, the clock records one tick. If the mirrors are separated by a fixed distance, the timing of the clock depends entirely on how long the light takes to travel between them. Now imagine this light clock resting on a table in a laboratory. To an observer standing next to the device, the light pulse moves straight upward to the top mirror and then straight downward again. The path of the light is vertical, and the time between ticks depends only on the distance between the mirrors and the constant speed of light. But consider what happens if the clock is placed aboard a spacecraft moving rapidly through space. To an observer inside the spacecraft, nothing unusual appears to happen. The light still travels straight up and down between the mirrors, and the clock ticks at its normal rate. However, an observer watching the spacecraft from outside sees something different. Because the spacecraft is moving sideways while the light travels between the mirrors, the light pulse follows a diagonal path rather than a straight vertical line. It moves upward and sideways at the same time, tracing a zigzag pattern between the mirrors. This diagonal path is longer than the simple up and down path seen by the observer inside the spacecraft. Yet the speed of light must remain the same for both observers. If the light travels a longer path at the same speed, then it must take more time to complete each tick. This means the moving clock appears to run more slowly compared with the clock at rest in the laboratory. This effect is called time dilation. Time dilation means that a moving clock ticks more slowly when viewed from a stationary frame of reference. The faster the clock moves relative to the observer, the more pronounced the effect becomes. At everyday speeds, the difference is far too small to notice. A passenger airplane travelling at several hundred kilometers per hour experiences only tiny fractions of a second of time dilation over the course of a flight. But when speeds approach the speed of light, the effect becomes dramatic. Particles travelling through accelerators at velocities close to the speed of light experience time passing far more slowly relative to stationary observers. This phenomenon has been measured countless times in modern experiments. One striking example involves particles known as muons. Muons are unstable particles created when high-energy cosmic rays collide with atoms in Earth's upper atmosphere. These particles have an extremely short lifetime. On average, a muon survives only about 2/millionths of a second before decaying into other particles. Given their brief lifetime, muons should travel only a short distance before disappearing, yet detectors at Earth's surface routinely observe muons created high in the atmosphere. The explanation is time dilation. From the perspective of observers on Earth, the muons' internal clocks run more slowly because the particles move at speeds close to the speed of light. This extended lifetime allows them to travel many kilometers before decaying. Time dilation has also been confirmed in laboratories, such as the European Organisation for Nuclear Research, commonly known as CERN. At facilities like the Large Hadron Collider, particles are accelerated to velocities extremely close to the speed of light. Sophisticated detectors measure how these particles behave and how long they survive. The results consistently match the predictions of Einstein's theory. But time dilation is only one piece of the story. Another consequence of special relativity is length contraction. When an object moves at high speed relative to an observer, the length of the object measured along the direction of motion appears slightly shorter. This effect might seem strange, but it arises naturally from the same requirement that the speed of light remain constant. If time intervals change for moving observers, then spatial distances must also adjust in order to preserve the relationship between distance and speed. Length contraction becomes noticeable only at extremely high velocities. For example, if a spacecraft were to travel at 90% of the speed of light, its length measured along the direction of motion would appear significantly shorter to an external observer. Inside the spacecraft, however, nothing unusual would be noticed. The astronauts aboard would measure the spacecraft's length as perfectly normal. Relativity ensures that each observer's measurements remain internally consistent. Another equally surprising consequence involves the concept of simultaneity. In everyday experience, two events that occur at the same time for one observer are assumed to occur at the same time for all observers. Relativity reveals that this assumption is not always true. When observers move relative to one another, events that appear simultaneous in one frame of reference may occur at different times in another. This phenomenon is known as relativistic simultaneity. The idea can be illustrated with a thought experiment involving lightning strikes along a moving train. Imagine two bolts of lightning striking the front and rear of a train at exactly the same moment as measured by an observer standing on a railway platform. For that observer, the flashes occur simultaneously. However, an observer sitting in the middle of the train is moving toward one flash and away from the other. Because light from the two strikes travels at the same speed, the observer on the train receives the flashes at different times. In this frame of reference, the lightning strikes did not occur simultaneously. This does not mean that either observer is mistaken. Each measurement reflects the geometry of space-time relative to the observer's motion. Time dilation, length contraction, and relativistic simultaneity all arise from the same underlying principle. The speed of light remains constant for every observer. To preserve this constant speed across all frames of reference, measurements of space and time must adjust accordingly. What once seemed like absolute quantities become flexible. Motion reshapes time intervals. Distance measurements depend on velocity. The ordering of events can shift depending on the observer's perspective. These effects are not mathematical curiosities. They are real features of the universe confirmed by decades of experimental evidence. Whenever particles approach the speed of light, relativity reveals itself. And through these remarkable phenomena, the constant speed of light continues to define the structure of motion, time, and space. One of the most famous insights in modern physics emerged shortly after Albert Einstein introduced his theory of special relativity. It appeared in a short scientific paper published in the year 1905, the same remarkable year that produced several of Einstein's groundbreaking works. In that paper, Einstein revealed a deep relationship between two quantities that had once seemed completely different: mass and energy. The relationship is expressed through a simple statement: energy equals mass multiplied by the speed of light squared. This expression is often spoken as energy equals mass times c squared, where the letter c represents the speed of light. At first glance, the equation looks deceptively simple, yet hidden within it is one of the most profound ideas in all of physics. Mass and energy are not separate things. They are different forms of the same underlying physical quantity. In classical physics, mass had been viewed primarily as a measure of how much matter an object contained. Energy, by contrast, was associated with motion, heat, or radiation. Einstein's relation showed that these two concepts are interchangeable. A small amount of mass can be converted into a large amount of energy, and energy itself possesses an equivalent amount of mass. The key factor in this relationship is the square of the speed of light. The speed of light is an enormous number, roughly 300 million meters per second. When that value is squared, the resulting number becomes extraordinarily large. This means that even a tiny amount of mass corresponds to a tremendous amount of energy. To get a sense of the scale, consider a single gram of matter. If that gram were completely converted into energy according to Einstein's relation, it would release roughly 90 trillion joules of energy. That is comparable to the energy produced by a large power plant operating for many days. Fortunately for the continued existence of our everyday surroundings, matter does not normally convert entirely into energy under ordinary conditions. Most objects remain quite stable. However, in certain processes, small portions of mass can indeed be transformed into energy. This phenomenon lies at the heart of nuclear physics. Inside the nuclei of atoms, protons and neutrons are bound together by the strong nuclear force. When atomic nuclei undergo reactions such as nuclear fission or nuclear fusion, a tiny fraction of their mass can be converted into energy. This released energy powers some of the most dramatic events in the universe. For example, the Sun produces energy through nuclear fusion occurring in its core. Hydrogen nuclei combine to form helium, and in the process a small amount of mass disappears. That missing mass emerges as energy in the form of electromagnetic radiation and energetic particles. Every second, the Sun converts about 4 million tons of mass into energy. That energy travels outward through space as sunlight, warming our planet and sustaining life on Earth. The same principle also operates in far more extreme environments. In exploding stars known as supernovae, nuclear reactions release immense amounts of energy as stellar cores collapse and rebound. In the violent surroundings near black holes, matter falling inward can release enormous radiation as gravitational energy transforms into light and high-energy particles. Throughout the cosmos, mass and energy are constantly exchanging roles. The speed of light sits at the center of this exchange. It acts as the conversion factor linking mass with energy. But the story does not end there. Light itself also carries energy, even though light consists of particles with no rest mass. These particles are known as photons. The concept of photons emerged in the early 20th century as scientists explored the quantum nature of light. In 1900, the German physicist Max Planck introduced the idea that electromagnetic radiation is emitted and absorbed in discrete packets of energy. A few years later, Einstein extended this concept while explaining the photoelectric effect, a phenomenon in which light shining on a metal surface can eject electrons from the material. Einstein proposed that light behaves as if it consists of individual particles, each carrying a specific amount of energy. The energy carried by each photon depends on the frequency of the light. Higher frequency light, such as ultraviolet radiation or X-rays, carries more energy per photon than lower frequency light, such as infrared radiation. This relationship can be expressed clearly in words. The energy of a photon equals Planck's constant multiplied by the frequency of the light. Although this relation involves another fundamental constant known as Planck's constant, the speed of light still plays an essential role. The frequency and wavelength of light are linked through the speed of light itself. If the wavelength becomes shorter, the frequency must increase so that the wave continues travelling at the same constant speed. Because of this connection, the speed of light quietly governs the behaviour of electromagnetic radiation across the entire spectrum. Radio waves, microwaves, visible light, ultraviolet radiation, X-rays and gamma rays all move through space at the same fundamental speed. What differs between them is their frequency and wavelength, which determine how much energy each photon carries. These principles play a crucial role in many areas of modern science. Astronomers studying distant galaxies rely on electromagnetic radiation to measure cosmic distances and temperatures. High-energy astrophysicists investigate gamma rays produced by extreme environments such as neutron stars and black holes. In particle physics laboratories, scientists accelerate particles to enormous energies and study the radiation they emit. Facilities such as the Large Hadron Collider at the European Organisation for Nuclear Research explore collisions between particles moving close to the speed of light. In these experiments, mass and energy transform back and forth in accordance with Einstein's relation. New particles can emerge from concentrated energy, and unstable particles can convert their mass into energetic radiation as they decay. Every one of these processes reflects the same fundamental principle. Mass, energy, and radiation are deeply connected through the constant speed of light. The constant c appears again and again throughout the equations of physics. It governs the propagation of electromagnetic waves. It links energy and mass. It determines the maximum speed at which information can travel. Whenever scientists explore the deepest layers of physical law, the speed of light quietly reappears. What began as a measurement of how quickly light travels through empty space has become a central feature of the universe's structure. The constant c is no longer simply the speed of light. It is one of the fundamental keys to understanding how energy, matter, and radiation interact throughout the cosmos. At the end of the 19th century, the wave theory of light seemed firmly established. Experiments involving interference and diffraction had demonstrated that light behaves like a wave, and Maxwell's theory had explained those waves as oscillations of electric and magnetic fields moving through space. Yet nature still had another surprise waiting. As scientists began studying how light interacts with matter at very small scales, they encountered behaviour that could not be explained by waves alone. One of the first clues appeared in the work of the German physicist Max Planck. In the year 1900, Planck was investigating a problem involving thermal radiation. Physicists were trying to understand how hot objects emit electromagnetic radiation across different wavelengths. This problem became known as blackbody radiation. According to classical physics, the intensity of radiation at short wavelengths should grow without limit, producing an infinite amount of energy. This prediction became famously known as the ultraviolet catastrophe, because the theory suggested that hot objects should emit enormous amounts of high-frequency radiation. But experiments clearly showed that this did not happen. Planck eventually discovered that the problem could be solved by making a radical assumption. Instead of allowing energy to vary continuously, Planck proposed that energy could be emitted or absorbed only in discrete packets. These packets were proportional to the frequency of the radiation. Planck expressed this idea through a relationship that can be stated clearly in words. The energy of a quantum of light equals Planck's constant multiplied by the frequency of the radiation. At first, Planck treated this idea mainly as a mathematical trick that made the equations work. But a few years later, Albert Einstein realized that the concept had a deeper meaning. In the year 1905, Einstein studied an experimental phenomenon known as the photoelectric effect. In this experiment, light shines on a metal surface and causes electrons to be ejected from the material. When physicists carefully examined the details of the effect, they noticed something puzzling. Increasing the brightness of the light did not necessarily increase the energy of the emitted electrons. Instead, the key factor was the frequency of the light. If the light frequency was below a certain threshold, no electrons were emitted at all, no matter how intense the light became. However, once the frequency exceeded that threshold, electrons were ejected immediately, even if the light was very dim. This behavior was difficult to explain if light behaved purely as a wave. Einstein proposed a bold solution. He suggested that light itself behaves as if it consists of tiny particles, each carrying a discrete packet of energy. These particles later became known as photons. When a photon strikes an electron in the metal, it transfers its energy to the electron in a single interaction. If the photon carries enough energy, the electron can escape from the metal surface. If the photon does not carry enough energy, the electron remains bound inside the material. This explanation matched the experimental observations perfectly. Einstein's interpretation showed that light possesses both wave-like and particle-like properties. In some experiments, such as interference patterns, light behaves as a wave. In others, such as the photoelectric effect, it behaves as a stream of particles. This strange dual nature became one of the defining features of quantum physics. Over the following decades, physicists developed increasingly sophisticated theories describing the behavior of light and matter at microscopic scales. The most successful of these theories is known as quantum electrodynamics. Quantum electrodynamics, often abbreviated as QED, describes how light interacts with charged particles such as electrons. It combines the principles of quantum mechanics with the electromagnetic theory originally developed by James Clerk Maxwell. The modern formulation of quantum electrodynamics was developed during the 1940s by several physicists working independently. Among the most important contributors were Julian Schwinger in the United States, Richard Feynman at Cornell University, and later the California Institute of Technology, and Shinichiro Tomonaga in Japan. Their work provided a consistent mathematical framework for describing how photons and charged particles interact through electromagnetic forces. In this theory, the electromagnetic field is treated as a quantum field that fills all of space. Instead of imagining photons as tiny billiard balls moving through empty space, quantum electrodynamics describes them as excitations of the electromagnetic field itself. An excitation is a localized disturbance in the field that carries energy and momentum. In much the same way that ripples appear on the surface of water, when energy passes through it, photons appear as ripples in the electromagnetic field. Whenever a charged particle such as an electron accelerates, it disturbs the electromagnetic field around it. This disturbance can propagate outward through space as electromagnetic radiation. Conversely, when a photon encounters a charged particle, the electromagnetic field interacts with that particle and transfers energy or momentum. Quantum electrodynamics provides a precise mathematical description of these interactions. The predictions of this theory have been tested with extraordinary precision. For example, measurements of the magnetic properties of the electron agree with the predictions of quantum electrodynamics to more than 10 decimal places. Few theories in science have ever achieved such astonishing accuracy. Within this framework, the reason photons always travel at the speed of light becomes clear. Photons are massless particles. According to the principles of relativity, particles with no rest mass must move at the universal speed limit defined by the structure of space-time. That speed is the same constant that appears in Maxwell's equations and in Einstein's theory of relativity. Because photons have zero rest mass, they cannot slow down or remain at rest. They always move at the speed of light in a vacuum. This property holds regardless of how energetic the photon is. A radio wave photon and a gamma ray photon both travel at exactly the same speed through empty space. What differs between them is the frequency of the electromagnetic wave and therefore the amount of energy each photon carries. In this way, the quantum theory of light completes a remarkable story that began centuries earlier. Light was first understood as something that travels. Later it was revealed to behave like a wave spreading through space. Then experiments showed that it also behaves like a particle. Quantum electrodynamics unites these ideas by describing photons as quantized excitations of an electromagnetic field, and throughout this entire description, one constant remains central. The speed of a light continues to define how disturbances in the electromagnetic field move through the fabric of the universe. For much of scientific history, empty space was imagined as exactly what the phrase suggests. It was simply nothing. A void separating stars, planets, and particles containing no substance and no activity. Classical physics treated the vacuum as a passive stage where events could occur, but where nothing happened on its own. Yet the development of quantum theory gradually revealed that this picture is incomplete. In the framework of modern physics, even the emptiest region of space is not truly empty. Instead, it is filled with fields. Quantum field theory describes the universe as a collection of fundamental fields extending throughout spacetime. The electromagnetic field, the electron field, the quark fields that form protons and neutrons, and many others all exist everywhere, even in places where no particles appear to be present. Particles themselves are understood as localized excitations of these fields. When a photon travels through space, it is a ripple moving through the electromagnetic field. When an electron moves, it represents a disturbance in the electron field. But even when no excitations are present, the fields do not become perfectly still. According to quantum mechanics, complete stillness is impossible. Every quantum system possesses a minimum level of energy that cannot be removed. This unavoidable baseline energy is called zero-point energy. Zero-point energy arises because quantum fields must obey the uncertainty principle. This principle, originally formulated by Werner Heisenberg, states that certain pairs of physical quantities cannot both be specified with perfect precision. One consequence is that fields cannot remain completely motionless. Even in their lowest possible energy state, they continue to fluctuate slightly. As a result, the vacuum is filled with tiny, restless fluctuations of quantum fields. These fluctuations are extremely small and occur over incredibly short timescales, but they are real physical phenomena. The vacuum, it turns out, is more like a restless ocean than a perfectly calm void. For many years, these fluctuations were considered largely theoretical. They appeared naturally in the equations of quantum field theory, but detecting their effects experimentally seemed extremely difficult. Then, in the year 1948, a Dutch physicist named Hendrik Casimir proposed an experiment that would reveal their presence. Casimir studied what happens when two very flat metal plates are placed extremely close together in a vacuum. According to classical physics, nothing unusual should occur. The plates should simply remain where they are. But quantum field theory predicts something more subtle. Because of quantum fluctuations, electromagnetic waves of many different wavelengths are constantly appearing and disappearing in empty space. These waves exist even in the absence of external radiation. When two metal plates are placed close together, they restrict the wavelengths of fluctuations that can exist in the narrow space between them. Certain wavelengths cannot fit between the plates, while others can. Outside the plates, the vacuum fluctuations remain unrestricted. Inside the gap, the allowed fluctuations become limited. This difference creates an imbalance in the pressure exerted by the quantum vacuum. As a result, the plates experience a small force pushing them together. This phenomenon is known as the Casimir effect. Although the force involved is extremely tiny, it has been measured in laboratories using delicate experimental equipment capable of detecting minute forces at microscopic distances. The Casimir effect demonstrates something remarkable. Empty space is not empty. It contains measurable physical activity arising from the fluctuations of quantum fields. These fluctuations form part of what physicists call the quantum vacuum. The quantum vacuum possesses properties that influence how particles and fields behave. For example, the electromagnetic field interacts continuously with virtual particle pairs that briefly appear and vanish within the vacuum. These fleeting pairs consist of particles and antiparticles that emerge momentarily from quantum fluctuations before annihilating each other again. Although their lifetimes are extremely short, their effects can subtly influence the behavior of electromagnetic interactions. One consequence is a phenomenon called vacuum polarization. In vacuum polarization, the presence of charged particles alters the structure of the surrounding vacuum. Virtual particle pairs respond to electric fields, modifying how electromagnetic forces propagate through space. These effects are predicted by quantum electrodynamics and have been confirmed through extremely precise experiments. Because the vacuum contains these fluctuating fields, physicists sometimes describe it as having its own structure. It is not a substance in the traditional sense, but it behaves as a physical environment influencing the propagation of particles and radiation. This raises an intriguing possibility. If the vacuum possesses measurable properties, then those properties may play a role in determining how electromagnetic waves move through space. In Maxwell's theory, the speed of light emerges from two constants describing the electromagnetic response of the vacuum. These constants represent the electric permittivity and magnetic permeability of empty space. Quantum field theory suggests that these properties arise from the behavior of the underlying fields filling the vacuum. The electromagnetic field interacts with quantum fluctuations and virtual particles, which subtly influence how electric and magnetic disturbances propagate. Although the overall speed of light remains constant in a vacuum, its value may ultimately be rooted in the deeper structure of these quantum fields. In this sense, the speed of light could be understood not merely as a property of electromagnetic waves, but as a consequence of the architecture of the quantum vacuum itself. The vacuum, rather than being a passive background, becomes an active participant in the behavior of the universe. This perspective forms part of the broader framework known as quantum field theory. Quantum field theory combines the principles of quantum mechanics with the insights of special relativity. It describes particles as excitations of fields and explains how those fields interact through fundamental forces. Within this framework, every particle and every interaction arises from the dynamics of quantum fields permeating space-time. The vacuum is the lowest energy state of the system, yet it remains filled with fluctuating activity. Even in the most empty regions of intergalactic space, these quantum fields continue their subtle motion. And through their presence, they help define how light and other massless particles move through the universe. The speed of light, once thought to be merely a measured quantity, now appears tied to the very structure of the vacuum itself. What once seemed like nothing has revealed itself to be something far richer. The quiet emptiness between the stars is alive with invisible motion, shaping the behavior of light across the cosmos. For most of human history, the universe was imagined as a vast but static stage. The stars appeared fixed against the night sky, and the galaxies beyond the Milky Way were not yet known to exist. The cosmos seemed enormous and mysterious, but fundamentally unchanging. This picture began to shift dramatically during the early 20th century. Astronomers using increasingly powerful telescopes started to realize that many faint smudges of light scattered across the sky were not clouds within our own galaxy, but entirely separate galaxies far beyond it. One of the key figures in this discovery was the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California during the 1920s, Hubble used a large telescope equipped with a 100-inch mirror to study distant galaxies. By measuring the brightness of certain stars known as Cepheid variables within those galaxies, he was able to determine their distances from Earth. Cepheid variable stars are extremely useful for this purpose because their brightness changes in a predictable way. The period of their brightness variation is directly related to their intrinsic luminosity. By comparing how bright these stars appear from Earth with how bright they truly are, astronomers can estimate how far away they must be. Using this method, Hubble discovered that many galaxies lay millions of light-years beyond the Milky Way. But he soon uncovered something even more surprising. When astronomers studied distant galaxies, they analyzed the light coming from them using a technique called spectroscopy. By spreading light into its component colors, much like a prism produces a rainbow, scientists can identify the chemical elements present in stars and galaxies. These spectral patterns also reveal how fast objects are moving relative to Earth. When a source of light moves away from an observer, its light shifts toward longer wavelengths. This effect is called redshift because the wavelengths move toward the red end of the visible spectrum. When Hubble and his colleague Milton Humason measured the spectra of many distant galaxies, they noticed a remarkable pattern. Nearly every distant galaxy showed redshift. In other words, almost all of them appeared to be moving away from us. Even more intriguing, The farther away a galaxy was, the greater its redshift tended to be. Galaxies twice as far away appeared to be moving away roughly twice as fast. This relationship became known as Hubble's law. It revealed that the universe itself is expanding. Galaxies are not simply flying outward through space like fragments from an explosion. Instead, space itself is stretching, carrying galaxies along with it. As space expands, the light travelling through it stretches as well. This stretching changes the wavelength of the light. Photons that began their journey as visible or ultraviolet radiation may arrive billions of years later, with longer wavelengths shifted toward the red, or even into the microwave region of the electromagnetic spectrum. This phenomenon is known as cosmological redshift. It provides powerful evidence that the universe has been expanding for billions of years. The speed of light plays a crucial role in how astronomers interpret this expansion. Because light travels at a finite speed, observing distant objects also means observing them as they existed in the past. Light from the sun takes about 8 minutes to reach Earth. When we look at the sun, we see it as it was 8 minutes ago. Light from the nearest stars beyond our sun may take several years to arrive. Observing those stars means seeing them as they were years in the past. When astronomers observe distant galaxies billions of light years away, they are looking billions of years into cosmic history. Telescopes effectively function as time machines, allowing scientists to study earlier stages of the universe. By analysing the light from distant galaxies, astronomers can reconstruct how galaxies formed, how stars evolved, and how the structure of the universe developed over cosmic time. One of the most important discoveries related to this early history emerged in the 1960s. During the late 1940s, physicists George Gamow, Ralph Alpher, and Robert Herman proposed a bold idea about the origin of the universe. They suggested that the universe began in an extremely hot and dense state. As the universe expanded, it cooled over time. If this idea were correct, then the early universe should have been filled with intense radiation. As the universe expanded and cooled, that radiation would stretch to longer wavelengths and eventually become faint microwave radiation, filling all of space. Gamow and his colleagues predicted that this leftover radiation should still exist today, as a faint background glow coming from every direction in the sky. In the year 1964, 2 radio astronomers working at Bell Laboratories in New Jersey stumbled upon exactly such a signal. Arno Penzias and Robert Wilson were using a sensitive microwave antenna designed for satellite communication experiments. No matter where they pointed the antenna, they detected a faint but persistent background signal. At first, they suspected interference from equipment noise, atmospheric effects, or even pigeons nesting in the antenna structure. After carefully eliminating these possibilities, they realized the signal appeared to come uniformly from all directions in space. At the same time, a team of physicists at Princeton University led by Robert Dick had been searching for precisely the radiation predicted by Gamow's theory. When the two groups compared their findings, the conclusion became clear. The mysterious signal was the cosmic microwave background. This radiation represents the cooled remnant of the intense heat present shortly after the universe began expanding. Today, the cosmic microwave background fills all of space with faint microwave radiation, corresponding to a temperature of roughly 3 degrees above absolute zero. The discovery provided powerful confirmation that the universe has evolved over billions of years. Once again, the speed of light plays a central role in this story. Because light travels at a finite speed, there is a limit to how far we can see into the universe. Even if the universe extends far beyond the regions we can observe, we can only detect light that has had time to reach us since the beginning of cosmic expansion. The region of the universe that we can observe is known as the observable universe. Its radius is determined by how far light has been able to travel during the age of the universe, which current measurements estimate to be roughly 13.8 billion years. Within that immense sphere lie hundreds of billions of galaxies, each containing billions of stars. Beyond that boundary may lie much more of the universe, but light from those regions has not yet reached us. The speed of light therefore sets the limits of our cosmic horizon. It determines how far we can see, how far information can travel, and how deeply we can peer into the past history of the universe. Every image captured by a telescope carries a message that has been travelling across space for years, centuries, or even billions of years. The universe reveals its history through the journey of light. As physics progressed through the 20th century, scientists began to notice an unexpected connection between several areas of science that had once seemed unrelated. Concepts from thermodynamics, information theory, relativity, and quantum mechanics were beginning to converge. At the center of this convergence was a simple but powerful question: how much information can exist within a physical system? This question may sound abstract at first, but information in physics has a very concrete meaning. Information describes the number of possible states a physical system can have. For example, the arrangement of molecules in a gas, the orientation of magnetic particles in a material, or the pattern of electrical charges stored in a computer memory all represent information. The more possible configurations a system can take, the more information it can contain. In thermodynamics, this idea is closely related to the concept of entropy. Entropy measures the number of microscopic configurations corresponding to the macroscopic state of a system. In simple terms, entropy describes how many ways the internal structure of a system can be arranged, while still appearing the same from the outside. The relationship between entropy and information became clearer during the 20th century, as scientists began studying the physics of computation and communication. But one of the most surprising insights into the limits of information came from the study of black holes. A black hole forms when a massive object collapses under its own gravity, compressing matter into an extremely dense region where gravity becomes so strong that not even light can escape. The boundary surrounding this region is called the event horizon. Once anything crosses the event horizon, it cannot return to the outside universe. At first, physicists believed that black holes might simply destroy information. Matter falling into a black hole seemed to vanish from the observable universe, leaving no trace of its internal structure. But in the early 1970s, a young Israeli physicist named Jacob Bekenstein began to question this idea. Bekenstein proposed that black holes must possess entropy. His reasoning was based on a principle from thermodynamics known as the second law of thermodynamics. This law states that the total entropy of an isolated system cannot decrease over time. If matter carrying entropy were to fall into a black hole and disappear without a trace, the total entropy of the universe could decrease, violating this fundamental law. To preserve the second law, Bekenstein suggested that black holes must have their own entropy proportional to the area of their event horizon. This idea was revolutionary. It meant that the surface area of a black hole encodes information about everything that has fallen into it. Later work by Stephen Hawking and other physicists showed that black holes can emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, confirmed that black holes behave like thermodynamic objects with temperature and entropy. Bekenstein took these ideas even further by proposing a universal limit on the amount of information that can be stored within a given region of space. This limit is known as the Bekenstein bound. In simple terms, the Bekenstein bound states that there is a maximum amount of information that can be contained within a finite region of space possessing a certain amount of energy. The bound can be expressed as a relationship between the size of the region, the energy contained within it, and fundamental constants of nature, including the speed of light. Although the exact mathematical expression is complex, the principle behind it is straightforward. Information is not abstract in the physical sense. It must be stored in matter or energy, and both matter and energy are constrained by the laws of physics. Because nothing can travel faster than the speed of light, information cannot be transmitted instantaneously across space. Every signal, every message, and every interaction between particles must respect this cosmic speed limit. This limit shapes how information flows through the universe. If a star explodes in a distant galaxy, the news of that event cannot reach us until the light from the explosion has had time to cross the vast distance separating us. If two particles interact in one region of space, their influence cannot instantly affect another distant region. The speed of light defines the maximum rate at which cause can influence effect. These limits become especially dramatic near black holes. At the event horizon of a black hole, the escape velocity equals the speed of light. Light emitted exactly at the horizon can barely hover in place before being drawn inward by gravity. Inside the event horizon, the geometry of space-time becomes so distorted that every possible path leads deeper into the black hole. From the perspective of the outside universe, information crossing the event horizon becomes inaccessible. The event horizon therefore acts as a boundary separating regions of space-time that can communicate from those that cannot. This idea extends beyond black holes to the universe as a whole. Because the universe has a finite age and the speed of light is finite, there exist regions of space that are simply too far away for their signals to have reached us yet. These boundaries define what physicists call cosmic horizons. Within our observable universe, information carried by light has had time to reach us since the beginning of cosmic expansion. Beyond that region, events may be occurring that remain forever hidden from observation. These cosmic boundaries are not physical walls. They arise naturally from the interplay between the expansion of space and the finite speed of light. The constant c, therefore, does far more than determine how quickly light travels. It defines the maximum speed of information transfer. It determines the causal relationships between events. It limits how much information can exist within a given region of space, and it shapes the horizons that divide the observable universe from regions beyond our reach. Through these connections, the speed of light becomes deeply woven into the structure of physical law. It links relativity, thermodynamics, and information theory into a single framework describing how the universe stores and transmits information. What once appeared to be simply the speed of light has become something much more fundamental. It is the speed at which reality itself communicates. By the time physicists reached the end of the 20th century, two towering frameworks had come to dominate our understanding of nature. One of these frameworks is quantum mechanics. Quantum theory describes the behavior of particles and fields at extremely small scales. It explains the structure of atoms, the properties of light, and the interactions between fundamental particles. The other framework is general relativity, developed by Albert Einstein in the year 1915. General relativity describes gravity as the curvature of space-time itself. Massive objects such as stars and galaxies bend space-time around them, guiding the motion of planets, light, and matter. Both theories have been tested with extraordinary precision, and both have proven remarkably successful within their respective domains. Yet they remain fundamentally different in character. Quantum mechanics describes nature in terms of probabilities, fluctuating fields, and discrete quanta of energy. General relativity describes the smooth geometry of spacetime shaped by mass and energy. When physicists attempt to apply both theories at the same time, difficulties arise. The mathematical structures of quantum theory and gravitational spacetime do not easily combine. One of the greatest challenges in modern physics is to develop a unified framework that incorporates both quantum mechanics and gravity. This goal is often called quantum gravity. Several approaches have been proposed, each offering a different way of describing the deep structure of space-time. One prominent research program is known as loop quantum gravity. Loop quantum gravity was developed through the work of several physicists, including Abhay Ashtekar and Carlo Rovelli. Their work suggests that spacetime itself may possess a discrete structure at extremely small scales. According to this theory, spacetime is not perfectly smooth. Instead, it may consist of tiny units woven together in a network often described as a spin network. These networks represent quantized chunks of space connected by links carrying information about geometry. At scales far smaller than atoms, space might resemble a microscopic fabric composed of these interconnected elements. If this picture is correct, then the smooth spacetime described by Einstein's theory emerges from an underlying quantum structure. Within such a framework, the speed of light may arise naturally from the fundamental rules governing these microscopic building blocks of spacetime. Another influential approach comes from a concept known as the ADS-CFT correspondence. This idea was introduced in the year 1997 by the theoretical physicist Juan Maldacena. A DSCFT stands for anti-de Sitter space and conformal field theory. Although the terminology sounds technical, the basic idea is deeply intriguing. Maldacena's proposal suggests that certain gravitational theories describing spacetime in a higher dimensional universe can be mathematically equivalent to quantum field theories defined on a lower dimensional boundary. In other words, a theory of gravity operating in a region of space may correspond exactly to a quantum theory without gravity existing on the surface surrounding that region. This surprising relationship has opened new avenues for exploring quantum gravity and the behavior of black holes. It also hints that spacetime itself may emerge from more fundamental quantum relationships. Another line of research explores the possibility that spacetime may not be fundamental at all. Some physicists, including Lee Smolin, have suggested that spacetime could be an emergent property arising from deeper networks of interactions. In this view, space and time might resemble large-scale patterns that arise from the collective behavior of underlying quantum systems. Just as temperature emerges from the motion of countless molecules in a gas, space-time geometry might emerge from microscopic quantum processes that do not resemble classical space at all. If this idea proves correct, then the speed of light could represent a limit emerging from the fundamental structure of those deeper interactions. The constant c would then reflect the maximum rate at which information can propagate through the underlying quantum network of reality. While most modern theories assume that the speed of light remains constant, some researchers have explored alternative possibilities. One intriguing proposal is known as variable speed of light cosmology. This idea has been explored by physicists, including Quomogeho. In these models, the speed of light might have been different during the earliest moments of the universe. If light travelled faster during the universe's infancy, it could potentially explain certain puzzles in cosmology, such as the surprising uniformity of the cosmic microwave background. These proposals remain speculative and are still being debated within the scientific community. Most experimental evidence continues to support the constancy of the speed of light, yet the exploration of such ideas demonstrates how deeply physicists are probing the foundations of physical law. The constant c appears in the equations of electromagnetism, relativity, and quantum theory. It governs how information travels, how energy and mass relate to one another, and how causality unfolds across space-time. Despite this central role, we still do not fully understand why the speed of light has the value that it does. It may ultimately be determined by the properties of quantum fields filling the vacuum. It might arise from the geometry of space-time at microscopic scales, or it could emerge from even deeper structures that modern physics has only begun to explore. Throughout the history of science, constants of nature have often served as clues, pointing toward deeper layers of understanding. The speed of light may be one such clue. What began centuries ago as a simple measurement of how quickly light travels across space has grown into a cornerstone of modern physics. Today, the constant c stands at the intersection of quantum theory, relativity, and cosmology. And as physicists continue to search for a unified description of nature, the speed of light remains one of the most important guides we have. It quietly marks the boundary between what is known and what still waits to be discovered.